Good morning, afternoon, or evening. To date in the course, we have studied how to use statistics to describe a population. So of course, if we have an entire population, we can describe it with precision. And how do we do that? The way that we do that is we try to get an idea of where's the central location of this population, where's this population centrally located in terms of some variable, and then we want to know how far apart is it typical for members of this population to be. Are they this far apart, or are they this far apart? So that is using descriptive statistics in order to describe a population. Secondly, we use statistics. In order to do that, of course, we have the measures of centrality, which are the mean, median, and the mode. And then we have the primary measures of variance, which is the variance, and then the standard deviation, which is square root of the variance. Then the second part was to use this knowledge to determine how, if we have a full population and we take a sample of that population, how can we use that knowledge to determine whether or not two groups of people are the same or different. So as you can see here, and that led us to two areas. One was to determine how to use a theory of hypothesis testing to determine whether things are true or not true of a population based on our knowledge of a sample. So we said that we have something called then a hypothesis, which is our alternative to what people currently believe. So this is sometimes called the alternative, and this is sometimes called the research hypothesis, and it's just as often simply called the hypothesis. And this is the alternative to what? It's the alternative to what is currently believed, which is the absence of this hypothesis, which is called hypothesis naught, or the null hypothesis. And two tests that we applied that kind of thinking to, one test is called the t-test, and the t-test is used to determine if two groups are different on some scale. For example, comparison of males and females, exempt, non-exempt employees, daytime, nighttime workers. So these are all areas where HR might be interested in determining if employees are different in on a certain variable based on their membership in a certain category. There are some times when you want to determine if three or more groups can be said to be different, and that is done using an ANOVA, or an analysis of variation. Hence ANOVA. So these are two tests of difference. Now that brings us where we are in terms of the third midterm examination, and that is to test for relationships. And the first of these categories is done where we don't know if one thing causes another thing, if they're both caused by something outside of our model. All we know is that this variable A and this variable B, we believe are co-related to each other. That is, A is related to B, and B is likewise related to A. And this is called, in statistics, a correlation. So the way you might think of it is this way. Here is this universe determined by the variability of variable A, and here's this universe determined by the total variability of variable B. So we have the total potential variability between the bounds of both variables. So now what we want to know is there any part of the variability of these things that are common to each other? We know there will be things that are not common to each other, but we want to know to what degree are things common to each other. And let's take an example that might be a true example that you could face in HR. So let's say we have this test that we use, and the test determines productivity. And the executive team has come to you, HR, and said, well, this test costs us a lot of money, so we're thinking of dropping the test. And as an HR practitioner, you say, we can't drop it because this test is too effective at helping us predict who's going to be a top performer or not. Otherwise, we're going to fall back to our own judgments and biases. So then the organization says, well, if you think it really works, why don't you show me that this test works? Okay, great. So let's say we have this standard. We have this standard for how well people do in this test, and this standard can go anywhere from a 1 to a 50. And then we have other measures of performance, and the performance measures can go anywhere from a 1 to a 10, conceivably. So now you randomly select data from the population of employees who have taken this test over, let's say, the past 3 years, and we have 10 subjects. So subject 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And for those subjects, we have these two measures. One is a measure of how they do in this test, and 2 is a measure of their performance. Now, before we do that, I want to hop over to take a visual look at what kinds of things we would try to notice if the two things were connected to each other. So let's say this is a result of the test, and this is a result of performance. And we know performance can be anywhere from a 1 to a 10, and the test grade can be anywhere from a 1 to a 50. So let's say we put people where they are on this test. So we look at the 10 people that we have, and one has a test score, let's see, this will be 20, 30, 40, 10. So let's say someone is right around a 20 and a 5, and another is at a point of a 5 and a 1. Let's make this a 0. 5 and a 1. And another person is at a 5 and a 2. And another person is at a 40 and a 7. And another person is at a 30 and an 8. And another person is at a 35 and a 9. And another person is at a 5 and a 3. And another person is at a 5 and a 2. And another person is at a 15 and a 5. And another person is at a 40 and an 8. So, just looking at this, if someone says to you, are these connected, does it seem like as something is happening with one, another thing is happening with the other, you would say this. I mean, visually, you can't help but do it. You would say, well, it looks like the higher you go on one, the higher you go on the other. That seems to fit the data pretty well. Now, the issue here is that you're using this knowledge of your sample to represent the population. So you're going to have to really be persuaded that this is not just something that you are assuming. You'd like to have a number that approximates how good this relationship is, how strong this relationship is. And the other thing you'd like to know is this relationship truly a plus relationship? As one goes up, the other goes up, and as one goes down, the other goes down. So is that a plus relationship? Or is there a negative relationship between these? That is, as one goes down, the other goes up. You see we're going up here. As this goes down, as we go down here, this goes up. And as we go from down to up, so we go up here, what is happening to these numbers? They're getting smaller, right? So we want to know, to the degree that we can, is this a positive relationship or a negative relationship? So now let's go to this sample data that we collected. And we do have a 20 and a 5 and a 5 and a 1. Let me make a 5 and a 1 and a 5 and a 2. And a 40 and a 7. And a 30 and an 8. And a 35 and a 9, and a 5 and a 3, and a 5 and a 2, and a 15 and a 5, and a 40 and an 8. That is exactly the same data that we posed right here. So visually, it looked like as one goes up, the other is up. As one goes down, the other is down. So it looks like they have a positive correlation, but let's see if we can figure out the magnitude of this correlation and if it truly exists. And how would you calculate that? Well, one of the things that you want to do is you want to, remember, you want to get an idea of how far this is, how far this is, and then you want to get an idea of how far the this times the this is. So the way you would get the bounds of the test, let's call this X. Let's call performance Y. The way you would get the bounds of the X would be taking X squared. And in this case, what is X squared? Well, one of the things that we would want to do is we want to first calculate the mean of the test. That is, your average person who takes this test gets a 20. Some lower, some higher. The average performance measure is a 5. Some higher, some lower. So now we want to take the difference between every measure and the mean, every subject and the mean, every observation and the mean, and we want to have something that we're going to call an X squared. We're going to also do the same for the other variable and have a Y squared. And then we need to have something called an X times Y. So, in order to do that, let's get the raw X's and Y's first. So you see the first observation is a 20, the average is a 20, so the difference X and the difference Y. The difference X here is a 0, and the difference Y here is a 0. Good. And for the second one, the difference here is between 5 and 20, or minus 15, and the difference in the second is 1 minus 5, and that difference is minus 4. With the next, the difference is between, again, 15, and the next one is 3 minus 5 minus 2. And the next is 40 minus 20. 40 minus 20 is a plus 20, and 7 minus 5 is a plus 2. And we do that for the rest. I'm going to fill in the rest here and then come back to you in a minute. Okay, here we are after calculating all the differences of the Y's and the differences of the X. Here we are after calculating all of the differences of the X's and the differences of the Y's. So now let's multiply these two numbers times each other. So 0 times 0 equals 0. And a minus 15 times a minus 4 is a plus 60. And a minus 15 and a minus 2 equals minus 30. And a plus 20 times a plus 2 equals 40. And I will do the rest. Okay, so here I am, and now I'm going to do the x times the x squared, the x times the x for the x squared here. So I'm just going to take this column and square it. So 0 times 0 is 0. 15 times 15 is 225. And conveniently, I don't have negative terms now. And 15 times 15 again is 225. And this 20 times 20 is 400. And down, doing the other numbers. And we go on. I will do the rest of the numbers and be back with you. Okay, so here I am, and I will do the same with this difference in y. I will square those numbers. So 0 times 0 is 0. Minus 4 times minus 4 is plus 16. Minus 2 times minus 2 is plus 4. 2 times 2 is plus 4. And this is so easy to do. We don't have to flip to any other side. We'll just do it straight down the line. Okay, so now we can calculate these. Oh, I'm sorry. Now let's calculate these totals, and the total of x times y's would be the, I beg your pardon here. This is supposed to be a 2. And then this is supposed to be a 3. Then this is supposed to be a 9. Yep, I have all my numbers right now. Okay, so the x times the y's, or the sum, this would be the sum of all of the x times y's equals, that's this column right here. Right here are the x, here are all the x times y's. We'll add them up to come to the sum of all the x, y's. And this is 370. The sum of all the x squares equals 2050. That's what we get by combining this column. Let's do it this way. By combining this column. And then the sum of all of the y squares is 76, and we got that by combining this column. The 76. Good. Now, what do we want to do with these numbers? We want to take the total variance, the total differences, which would be this would be called the correlation of x and y. That will equal how much they vary together, which is this x times y. We know what x times y is. It's right here. We got that by adding the sum of squares, by calculating the sum of squares of all of the xy pairs. So that equals, we know what it equals 370. And we want to divide that by the total sum of squares differences, which is this times this. The x's times the y. So we want to take the x, we want to take the sum of all the x squared, and we want to multiply that times the sum of all the y squared. And then because we're squaring, we want to take the square root of that. That's going to be in the denominator. So we know the top, the numerator is we know that the numerator is this thing right here, and we know that the denominator is going to be, let's see, what's the sum of all the x squares? It's right here. It's that 2050 times, what's the sum of all the y squareds? It's right here, the 76. And now we want to take the square root of that, which equals 370 over, this is 155,800, which equals 370 over, take the square root of that, 155.8, and you get 394.7. And now, what does that mean? That means the degree to which they vary together, this thing right here, compared to the way the potential for variance being independent from each other is 394.70. I shouldn't say independent. Having anything to do with each other or not with each other is this 394.7. So what do we know? We know that this is a positive correlation, right? 370 over 394. It's a positive correlation, and if you do the arithmetic, you get 0.937. What's the total that it can be? As high as a 1. What is it? A 0.937. That's pretty big, isn't it? Looks like it. Let's see how big it is. So now what you would do is you need to figure out the significance of this R that you came up with of, what's the R that you came up with? 0.937. All right, how do we do that? We take a t, because we're trying to compare our test here. Our test statistic is this, is going to lead us to our significance number, and that's going to equal R times the square root of n, and you're going to subtract 2 units of freedom, degrees of freedom there, and then you're going to take the square root of 1 minus R squared, and then just plug in the numbers. So this is a 0.937. What was Rn? Rn was 10. What's 10 minus 2? That's 8. Square root of 8. What's in the denominator? 1 times, what's R squared? So R squared is 878. So it's 1 minus 1, right here, minus R, or this number, squared, which is this number. And then we want to take the square root of that. So that equals, if you do the arithmetic, 2.65, and in the denominator, it's the square root of 0.122, which equals a 7.59 t of 7.59. Now, what I'm going to tell you here is that normally at this point you would go back to a t-table in order to look at whether or not a certain t is significant or not. So you would look at degrees of freedom, n minus 2. Look at this for the 7.59 with n minus 2, or 8 degrees of freedom. And what you will see there is that the likelihood of coming up with this t is less than 1 in 100 cases. So it's below 0.01. Therefore, what do we claim? We claim, yes, there is a degree to which we believe these variables are correlated. Remember, that's this line right here. They are correlated, and it is significant. Therefore, we can reject the null. So, that is a long and a short of doing a correlation, performing a correlation. This is what I can tell you generally. I will not ask you to do this, to come up with a t. But I will tell you what the standard is. So, for example, I will tell you that in order to conclude that there is a correlation, the R value has to be better than, let's say, 0.60. And then you would say, this is better than 0.60. So it is significant, and we would reject the null. By the way, it could also be better than minus 60. So this is actually lower than 60. This is higher than 60. But what we would say in that case is this, that the magnitude of the difference is 0.60. The directionality of the difference is this is negative, but the magnitude of the difference is 0.60. And that would lead us to this saying that, therefore, there's a relationship between these two variables. Now, I want to take these same numbers and I want to put them into SPSS, and so let's see what happens here. We will go to okay, so let's put these variables in here. So we have this one variable called test, which is a 20 here and a 5 for the second one, 5 for the third, 40 for the fourth, 30 and a 35, then a 5 and a 5 and a 15 and a 40. And so we have the 10 there. And then let's get the measures for the performance, which is a 5 and a 1 and a 2 and a 7 and an 8 and a 9, 3, 2, 5, 8. So we have all the variables plugged in, and let's call the one the test, and let's call the other variable performance. And so now we have our SPSS data file. So now we'll go back to data view. Now we'll go to data view and go to analyze, and we want a correlation. We want a bivariate correlation because it is the variation of two variables or each pair of variables, and we want the correlation between these two things. And if I remember correctly, it should be pretty big, right? We want to click on the Pearson correlation because this is what we're computing. Technically, it's called the Pearson product moment correlation product. Why? Here's why. Because we're multiplying the product of the difference in X versus the difference in Y. That's why it's product. And moment, why? Because we have measures of these two things at the same moment. We don't say that one causes the other or anything like that. It's just at the same moment. And this brings us with our correlation between the two. And we can see that the correlation between the two is just as we had computed. It's in this box right here. It's 0.937. And it's significant to the tune of 0.000, which means that's our likely error. 0.000. Well, of course, 0.937 captures a lot of course, 0.937 carries a lot of covariation, so we would assume that it would be significant. And indeed it is. So what would we say there? We would say that we have significant statistical evidence to support the research or alternate hypothesis that these two things are connected. And what conclusion then would you reach? The conclusion you would reach is, boss, we can't get rid of this test. It is too good. It's very, very, very good. How likely are we to be making an error based on these 10 measures that we got? Well, I'll tell you what, less than 1 out of 100 chance. We are really pretty sure. So you would not then, of course, drop the test. Everything else being. So that is how you correlate a correlation between two variables. Now, here is what would happen if you had some other variables. So let me just put some random numbers here. Oh, let me do this. Yeah. All right, so I just plugged in a couple other variables just for the heck of it, and we'll call it dummy 1. Oops. Dummy 1, dummy 2, and now let's, as we did before, let's do a bivariate correlation. Let's put dummy 1 and dummy 2 in there. And so we have this table now. So now let's look at this correlation table that we just produced. As we did in class, I want to point some things out to you. Oops. I want to point some things out to you. Let me copy and paste this. Okay, so I just clipped that file. There we go. So I just clipped that file, and here it is. So what kinds of things can we notice about a correlation table? Here's some things that we should be able to notice about a correlation table. Number one, see down the diagonal here? We have a 1, a 1, a 1, and a 1. Going down the diagonal are all 1s. Why is that? Because going down the diagonal, we have everything correlated with itself, right? Test and test, correlation of 1. Performance and performance, correlation of 1. Dummy 1 and dummy 1, correlation 1. And why is that? It's because everything is perfectly correlated to itself. When A goes up, guess what happens to A? It goes up. If it goes up 5%, 5 units, 5 anything, what happens to it? It goes up 5%, 5 units, or 5 anything. Here's another thing that we know. If you see if you want to know the correlation between performance and the test, it's the same as between performance and the test. So why are these the same? The reason these are the same is because they're the correlations between the same two variables. So whether you do it looking from one perspective or the other perspective, a correlation does not have anyone's particular perspective in mind. It's just the point at which they agree. So that is 0.937. What we see here also is we see correlations that are significant, and in SPSS, for example, you will see that they're flagged with an asterisk. And you see the significance here. The significance here is 0.12. So there is a significant, no sign, it's assumed to be a positive relationship between test and dummy, right here. It is possible for two things to be negatively correlated. So I'm just going to fake something here, and I'm just going to make this a negative 0.725. So what would we say here? We would say that the magnitude or strength of the relationship is 0.725. And we would say the directionality of the relationship is that these two variables are negatively correlated. And that's what you'll have to know. I'm going to post this first, and then I'll be working on producing the other relationship test tonight. The other relationship test, of course, is a regression. This is not a regression. We've often heard the phrase, correlation is not causation. This just means that the two things are related. One does not come first. One does not lead to another. In this test, we're trying to see if there's a relationship. If there is a relationship, then you might be interested in knowing if one causes the other, particularly if you could logically reach that conclusion. Then you would do a regression. For the sake of a correlation, our business is done here now. I'll see you in another video.